Okay. Yeah. So yesterday we have started a new topic, which is linear transformation. So linear transformation will use these two concepts, which we have already done, column spaces and null space. As we know that the column space and null space both are subspaces of vector space Rn and Rm. So yesterday I was just matrix of dimension m cross n with columns a1, a2, an. Column space is actually b, all b, where b actually is satisfying b equal to ax. That means b is actually linear combination of all a1, a2, an, which is like the vectors in columns, and therefore we actually say that column space is nothing but span of a1, a2. So it's a span of all columns. And since it's a span, it is also a subspace, because there is a theorem which we have seen earlier that every span is a subspace. And this column space, when we were doing earlier, we saw that it is actually, when you solve that, these vectors are actually of dimension Rm. Therefore column A is a subspace of Rm. Similarly, null space for a matrix M cross N with columns A1, A2, An, null space is what? It is actually the solution space of a homogeneous equation, which is Ax equal to 0. So when we are finding the column space, we are actually trying to find the columns.
भाई जर्मन का आया भाई
What was that? Yeah, so we are on null spaces, and I'm saying that for null spaces, why these messages are appearing here? Right, so for null space, we are actually solving a homogeneous equation, and null space is nothing but the solution space of homogeneous equation. And we have seen earlier that when we solve this x1, x2, xn, this actually comes out as a subspace of Rn. And using those definition, we can always prove that null space Ax equal to 0 is actually satisfy those three properties of subspace, and therefore it is a subspace of Rn. Now I just took one example, 1, 0, 1, 0. What will be the solution space of this matrix? Now this matrix has only one pivot, therefore there is one free variable, and therefore you actually can write x1 plus x2 is 0, and therefore your solution space becomes this, -1 and 1. Now when we are doing this Ax equal to b, this matrix actually corresponds with some linear, the matrix A actually corresponds with some linear transformation, because what we are actually doing is, if the matrix determinant is non-zero, it is invertible, then what we can do is we can find this x as A inverse b. And therefore what we are actually, the entire concept of transformation comes from here, that we are actually multiplying b with the transformation A inverse, so that it gives you another vector which is b, x. So for example, if you have a system of linear equation and the inverse of that matrix exists, then the solution coming from here, and therefore it is said that every system of linear equation has some kind of linear transformation associated with it. Now to give a better example, we in generally when this idea of transformation comes from functions. Now functions are used everywhere in mathematics. And what is this function? Function is when we are using that, when you have some space here, you transform or you define a function on x such that it takes you to another space y. Now a good example which I have taken yesterday was from probability, which you must have not done, but it explains it very well, that when we are in probability and when we are talking about tossing of coins, so what we do is actually we are on this space which is like t h h t, right? So first time when the coin is tossed, it is for t or h. This is my sample space. If the two times a coin is tossed, then it can be TT or HT or TT. Like the first time is it tossed, T comes, another times TT. So this is my this. Or HT can come TH. So this entire four can be the four possible choices when a coin is tossed four times. Now this makes your sample space. But when we want to do any kind of uh, thing on this, we actually cannot deal with the sample space, because if we are tossing a coin 100 times, then this becomes very large. Now what we do is, to narrow down this, what we do is we actually define, we take x as a random variable which takes only the number of heads. So a random variable is defined which actually says x0, x1, x2, because it is now easy to handle this, because now it is, we have one variable here. Now these random variables are taking value x is equal to 0 when you have a 0 head, this first case. When you have one head, because x is on the number of heads, when you have one head, x is 1. So these two cases when you have one head, and x is equal to 2 when you have two heads. Now what is done here is, using this function f, we are actually from x, where this you are on the random variable, you are actually going into another space y, which is real line. So this is actually called mapping in general. So what we are doing is, we are mapping x to a real line. And what is the purpose of doing this is, now I want to define this. When x is 0, what is the probability? When x is 0, probability is this, 1 by 2 into 1 by 2, so 1 by 4. Next is 1, I have two choices, 1 by 4 plus 1 by 4, so therefore 1 by 2. Now what has happened is, that is this variable which was actually on x 0, 1, 2 space had actually transformed into a real line, this 1 by 4, 1 by 2 and 1 by 4. And that's how we define a probabilistic space. Now, this was an idea to tell you how these functions are used from one space to another. Now we are using transformations. Now, what are these transformations? So, for example, T is a transformation, and we know that we are on vector spaces. So, what we are doing is, we are defining a transformation from a vector space V to W, and this transformation is T. Now, since we are on linear algebra, what we are doing is, all the there can be many transformations, as there can be many functions, but we are only interested in those transformations which are linear. Now, what linear means is that you are actually defining a transformation T from one space to another. Now, these spaces can be from R2 to R. So, for example, R2, you know, right, that you have a vector which has like two tuples, ordered pair x1 and x2. Now you are actually transforming it to another space which is R. That means you are taking a vector of R2 to a scalar. Now to qualify something as a linear transformation, so transformation, you understand that we are going from one space to another. To qualify something as a linear transformation means it's a linear, T is linear. There are two properties which it has to satisfy. This one, that if you take a scalar multiplication of that vector and take a transformation on that, that will be actually equal to scalar of TV. And the other one is, when you are taking a transformation on their sum, that will be actually the sum of the two transformations. So that's how it is, that a linear transformation will satisfy these two properties. Now then, I have taken yesterday an example. What is, there can be, we in the now on, I mean now when I'm doing the class, I will take few more example when a transformation is linear. So this one we took yesterday is a very good example when the transformation is not linear. So for example, I am on T and I'm taking this R3 to R. Now one example is, you have R3 as V1, V2, V3, and you take R to this is what its distance. A vector has, if vector is v1, v2, v3, its distance will be under root of v1 square, v2 square plus v3 square. Now this is actually the distance of that vector, and if I take the distance, if the transformation is defined this way, then this is not qualified as linear transformation, because it is not satisfying the first property itself. So for example, if I take t minus 2v, because it's a model, this under root here, the minus will not come out, so this will not be equal to minus 2v, and therefore it is not a linear transformation. There are many other examples which I will take today, and this one is, there I have a linear transformation from R2 to R3, right? You are all getting me?
Yes, ma'am.
Yes, ma'am.
Okay, yeah, so so then another example, that T is a linear transformation from R2, a vector space R2 to R3, and how it is defined? It is defined as V is a vector which is taken in R2. So you know it, that it should be V1 and V2. A vector defined in R3, it's a 3 tuple, and therefore it should be like this. And the way the transformation is defining is that, what is T doing is, it is taking V1, V2 to another space, third 3 space, I mean R3 space, in such a way that these values are now changed to this. So that is the entire purpose. It takes you to some another space. Now, a question is it a linear transformation? So we have to see the first property. Now the first property says TCV should be equal to CTV. This is simple example. I'll take more examples. So if I take TCV, it is what? CV. So what first you have to see what is CV. What is CV is this. CV2, CV1 plus V2, CV1 minus V2. This one. C can be written outside, therefore this becomes CTV. Therefore TCV is equal to CTV and first property is satisfied. The other property TV plus W should be equal to TV plus CW. Now I take another vector which is V and W. There are two vectors, so we have to take V1, V2 and W1, W2. Now you write V plus W as V1 plus W1, V2 plus W2. Right, so this is how I'm writing the sum. Now if you take TV plus W, it should be this one, right? Because the transformation is saying the first element is V2, then it is V1 plus V2, and then it is V1 plus V2 or minus, I think. 1 minute. Yeah. So this is V1 minus V2, next one. So what we are doing is we are just writing is these are simple ones. So then it is proved that it's a linear transformation. Now I said that when we are taking this transformation, now if we go back to what we have been doing on null spaces and sample space, column spaces, then we have to go back to that Rn and Rm space where we were earlier. Now, so let T be a transformation which is actually from Rn to Rm. So linear transformation of vector space TV can be written as M cross N matrix. Now, what it is doing is that now when you have a matrix which is defined as M cross N matrix and you have a T transformation, then this TV can be written as AV. How this is written, I'll just show you. So in order to get this matrix A, all we must do is to transform the standard basis of Rn, and that will make up the columns of our matrix A. So for example, we have this TR2 to R3 and TV is defined as this. Now, what is standard basis vectors? You know it, right? When we are in R2, it is 1 0 0 1, and when we are in R3, we have 1 0 0 0 1 0 1 0 0 1. Now here we are also trying to understand what is ordered basis pair. Ordered basis pair are this when you are this 1 0 0 1 and 0 0 1. This is also a basis, but this is not ordered. So now when we are actually transforming a transformation into a matrix form, we need ordered basis pairs. So for example, coming from the previous thing, T10 can be written as 011. From where this is coming? Because the transformation is defined as this one here. So if V vector is my basis vector 1 0, so what will be this? This will be 0 1 1. And if I take 0 1 in that transformation, 0 1 here, then this will be 1 1 and 1 minus 1. Right? So this will be how I will write T10 and this. Now these two vectors in R3. Who is doing this entertainment in between? Yeah, so where I was here. So now what we have done is T10 can be written as this, T01 can be written as this. Therefore, A becomes your column vector this. And if I write A into V, above I said that we can write TV is equal. You don't want to do class today?
Ma'am, someone joined from outside, I think.
How somebody can join outside from outside?
Ma'am, this Balwant Rai is not in our batch.
He had
In ma'am,
his
almost
classes also.
previous month also this person joined in some other course and
Balwant
he was
Rai.
here directly.
Yes, ma'am.
No, but how he
Yes, ma'am.
got the link? And even in the group, WhatsApp group also, I have seen somebody from outside is joining. Why are you sharing this group with other students?
Ma'am, I think someone has changed his name and then joined.
Anyways, so what I'm saying is that we can write this TV is equal to AV, and from where this A comes, we have seen that A is coming from here. So if you multiply A into V1, V2, we go back to this V2, V1 plus V2, which is nothing but TV. Therefore, we can prove that TV is actually equal to AV. Now, why is it we are doing? Because we need this matrix A. Now we will learn about linear transformation of matrices, because we have to again go back to those spaces which we were doing, and those column space and null space will now have different terminology, but we are using it now. So that will be image and kernels, which we have to do. So that's it. No, there are some more things here. Yeah, so there is one more thing I want to tell you, that now when you see different books, when we're writing a linear transformation T R2 to R2 or any space, sometimes in some books or in questions also I've seen that they use this form. I mean, notation is this. So when you write T x1 x2, which is actually, so in ordered pair, sometimes it is written. So but even if when it is coming in this form, you know that we can write always as T x1 as a square brackets, and these two notations are same, and in some books they are using the first notation. So this one is another thing, prove that T is a linear transformation. Oh, every 1 minute. So then we said that every linear transformation is associated with the matrix. Who is Balwant Rai here? So Balwant is not in your class.
No, ma'am.
No, ma'am. No,
How
ma'am.
he
Balwant
has
is not
joined
in our
it?
class.
No, but how he has joined it? Who has shared the link with him?
Ma'am, it could be someone from the class who has changed his or her name.
Okay.
Ma'am, someone,
Next.
Sarita, shared me the link.
What? Anyways, I see I have something to cover today. So then you have earlier we have seen that if you have this v1, v2, vn as a basis vector, then any vector v can be written as a linear combination of these vectors, right? So we know that. Now if we take the transformation on this becomes tv is equal to ct1 and so on, because it's a linear transformation. Now if you have a vector v which is 3 2 4, then this vector 3 2 4, if we want to take it to the matrix level, then 3 2 4 actually can be written as 3 bases, 2 bases, and 4 this. Now this will be used in questions now which I'm doing it, so you just need to know. And also I was telling you yesterday that when we are writing this v is a equal linear combination of c1 v2 vn. Now these c1 c2 cn, which we know that these are scalars, in some places people are using them also as a coordinate vectors. So it's just a name. You should know that somewhere the c1 c2 are used as a coordinate vectors, and now onwards when we are using these ordered basis pairs, right? So now today's class I want to do this, that when we have a linear transformation from one space to another space, we are actually taking it to Rn to Rm. And this is when we take this tx in Rm, because if we have a vector x in Rn, then tx will be in Rm, and it is called the image of x, right? And the set of all tx is also known as range of t. Now in this we will be doing what are the image of X, what are the ranges, and there is one more kernel which will come when we are going to back to those null spaces. So that kernel comes. So these are the three things which I have to cover in linear transformation. And yesterday I also did this because this is also needed at some point. And that if you have a linear transformation U to V, then B is a
मैम आप इसे बाहर कर सकते हो, किक आउट कर दीजिए।
कर रही हूँ, 1 मिनट मैं इसको वो
मेल आईडी नहीं देख सकते उसका?
यस मैम,
मैम आप सबको म्यूट कर दो।
म्यूट भी कर सकते हैं, किक आउट।
mute everybody. You can mute everyone.
यस मैम।
हाँ मैंने किया है इसको। But this is really bad, no?
Sarita shared me the link.
मैम इसको म्यूट करके लॉक कर दीजिए अनम्यूट ऑप्शन को।
अब गायब हो गया।
वो थोड़ी देर में फिर लॉगिन होता है ऐसी बीच बीच में।
But this is really bad. Who is this person?
मैम वी डोंट नो एक्चुअली लास्ट सेमेस्टर में भी ये हरकतें करके गया है।
Anyways, मैं क्या करूंगी, मैं इस अच्छा ये तुम्हारी क्लास का ही है तो पता नहीं मुझे, क्योंकि मैं अदरवाइज दूसरा लिंक जनरेट कर देती।
मैम अभी के लिए आप जो अनम्यूट का ऑप्शन है वो लॉक कर सकते हो।
कहाँ पे?
मैम आई थिंक ऑडियो में आता है कि सबके माइक्स अगर आप अनम्यूट करने से मना
अनम्यूट कर दूं।
करें
1 मिनट 1 मिनट।
हो जाएगा मैम, बट फिर हम क्वेश्चंस नहीं पूछ पाएंगे ना बीच में।
म्यूट ऑल ऑप्शन।
क्वेश्चन के बाद पूछ लेंगे ना।
तो मैं 1 मिनट
मैम
मैं
लेक्चर के
म्यूट
बाद कर दीजिए वो फिर वो अनलॉक फिर हम पूछ लेंगे।
हाँ हाँ मैं कर दूंगी, म्यूट कर दिया मैंने सब। Okay, so I was here. You can hear me. Just write a chat. You can hear me, right?
मैम अभी तक म्यूट नहीं हुए हैं सारे लोग।
अरे मैंने अभी तो म्यूट किया।
मैम बट मैं तो आपको ऑडिबल हूँ ना।
मैम you have to put a lock.
लॉक करना पड़ेगा।
वो हम अपने हाथ से अनम्यूट भी कर सकते हैं।
Ma'am, actually you need to lock the option of unmuting.
म्यूट ऑल ऑप्शन,
Yes, ma'am.
म्यूट अलाउ। अच्छा वेट ये मैंने कर रखा है अलाउ। अब नहीं होगा, वेट। अब बोलना तुम में से कोई।
हेलो मैम, आ रही है आवाज?
हाँ, म्यूट ऑन एंट्री। ये क्या हो रहा है? म्यूट ऑल ऑप्शन म्यूट सबको कर दिया मैंने, अभी भी आ रहा है। एनीवेज, अब मैंने ये मैट्रिक्स में बता रही थी दैट इफ यू बी हैज u1 u2 un and b dash is another this, then we can actually write this. Okay, so if you have understood this, I have one question for you. Functions that I wanted to tell you more examples where functions that are not linear transformations. Right, so one such example is f of x is equal to sin x. Yeah, can you prove this is not a linear transformation? Then function equal to x square is not a linear transformation. Can you prove this? Karo. So you are all muted, right? I cannot hear you. Okay. So sin x is, or I have even one better question. This one. Tx equal to sin x, xy, and cos y. This is not a linear transformation. So these are the three examples. So just see if you can do. Also, I have one more example. T x1 x2 equal to x1 x2 x2. This is also is not a linear transformation. Okay, we still have time, so try if you can do. Otherwise, I will do. Right, then I'm writing few more things. Until then, you just try. You are trying, right? Show that linear transformation. Kushagra, you wrote something I could not read. Show the linear transformation. No, I am not speaking. What happened to my here? So are you able to do those questions? My God. Now who is doing this? Okay, so answer to this question is we can take V as a vector x, y, and R R cos alpha, R sin alpha. Yeah, we can write this where L is your length of V and alpha is the angle from the positive x-axis. This here alpha, right? So what we can, this TV is actually this cos theta minus sin theta and cos theta xy. If I write this is cos theta minus sin theta cos theta, and xy we have written as alpha cos alpha r cos alpha and r sin alpha. Hello. Oh my God, I don't know what he has done. Oh, 1 minute. Okay, मेरे को okay. Yeah, now can you see my screen? Hello. Now can you see my screen? One minute, yeah. What is happening here? हेलो. एक्चुअली मैंने उसको तो निकाल दिया, कुछ एक्सपेल करने का ऑप्शन था, मैंने उसको किया. ओके ओके, मैं अनम्यूट भी कर रही हूँ. वेट. Wait a minute, I'm just unmuting you. कहाँ गया? Yeah. I think I have removed it.
बलवंत राय का ईमेल नहीं देख सकते हैं क्या?
नहीं, मैंने उसको actually there was an option to expel him. वो
मैम
मैंने अभी
एक्सपेल तो कर दिया, बट वो दोबारा भी ज्वाइन कर सकता है। मैम एक्सपेल कर दिया, लेकिन उसके बाद लिंक है, वो चाहेगा तो फिर ज्वाइन कर लेगा।
हाँ, अच्छा क्या करूँ मैं?
हम
ईमेल
पुनीत सर को बोलिए, उनको पता होगा कैसे देखते हैं या क्या करना है।
अच्छा पूछूंगी, बट फिर वो उसका ईमेल होना चाहिए ना उस लड़के का।
हाँ मैम, उनको पता होगा
मैम
ईमेल
अगर
के, मैम बिकॉज
आप
हमें ईमेल से तो
एंट्री
रजिस्टर
तभी
करना ही
देता है
पड़ता है।
वेबएक्स, जब आप अपना ईमेल आईडी दोगे तो ईमेल
यस
आईडी
मैम,
कुछ ना कुछ तो
ईमेल तो
लॉगिन
मिल ही
दिया होगा
जाएगा।
उसने।
हाँ
ईमेल
मतलब
मिल
अभी वाला
जाएगा
सेशन
उससे।
आप रिकॉर्ड कर, मतलब आज वाला सेशन है, ये डेट आप याद रख लीजिए, और मैम पुनीत सर से आप बोलेंगे तो फिर वो देख लेंगे कि मतलब कौन किस नाम से लॉगिन
हाँ
किया।
हाँ हाँ, ठीक है,
हाँ
मैं बोलूंगी उसको। ठीक है, ये मैं कर रही थी क्वेश्चन। So this one I was doing this one. So what it says is that you have a matrix A which is this
मैम प्लीज
form.
शुरू से बताए, बिकॉज हमने तो कुछ भी नहीं देखा।
Okay, I wrote these three questions that these three transformations are not linear transformation. Are you able to prove they are not linear transformations?
Yes, ma'am.
यस मैम।
All of you have done? Okay.
Yes, ma'am.
Okay, so because when we are doing these like this way, we can actually take some case also and say that, for example, here we can simply say this also 2 1 1 is actually equal to 4 2, and this is not equal to 2 t 1 1. So if it's just a 1 mark question, then we can simply take one example and say that, because if something is not valid for one example, it won't be valid. So then for this example, it is showing that this one is not a linear transformation. And similarly, in case of this one sin x xy case, you can take one example and show that, for example, here we can say that t2 pi pi is actually equal to t2 pi pi, and this is equal to sine 2 pi into 2 pi and cos 2 pi, and this is actually equal to 0 4 pi square and 1, and this is not equal to if you take 2t pi pi. So this is not equal to if you take 2t pi pi, because this will become equal to 0 2 pi square and minus 2. So then we can say that this is not a linear transformation. Now about this question, it is saying that notes that I have shared with you, reference notes, there in the introduction part of linear transformation, they are taking some good examples and they are showing the examples of linear transformation. So one good example they have shared is like if you have an image and if you want to transform it into an image which is rotated. So if you want to do this rotation, what we have to do is you have to actually perform a linear transformation such at an angle of theta. So that example I've taken from there. So an image can be rotated with a linear transformation such that this example, that it has the property that it rotates every vector in R square counterclockwise about the origin through the angle. So this is actually saying if you have an angle here, it actually rotates you at the angle of theta. So there in the image they are showing how it has rotated the image. Now to prove this, we can take a vector v which is equal to xy, and since here we are on the polar coordinates, so these xy can be written in form of r cos alpha and r sin alpha, right? And here tv is actually equal to, so this is your transformation t into xy. Transformation t is given tv is equal to av, so we can write av. So this we are writing, and if we multiply, this becomes this, and if I open this, this becomes r cos theta cos alpha minus r sine theta sine alpha r sine theta cos alpha plus r cos theta sine alpha, and this can be written as r cos theta plus alpha and r sine theta plus alpha. Therefore, this whole thing is actually rotated. This earlier it was only alpha, now it is theta plus alpha. So the transformation can do this. That is the example. Right now, I have to do a few more things. This is break, right, after this class, or you have another class?
We have lunch break after this class.
Yeah, so I
There
can
is
take
break
10 more
after this.
minutes. So I can take 10 more minutes.
Yes, ma'am.
Yes, ma'am, sure.
So you can do this later on, but t is r square to r. So you will take u as u1, u2, and v as v1, v2. And you will see just that there should not be any confusion between v1, v2, and because there are 4 variables. Now, as I said that every linear transformation is associated with the matrix, and as we have to go back to the so I have to do something more on the matrices part, but before that there is a note here that f of x equal to x plus 1 is called a linear function because its graph is a line. Yeah, but it's not a linear transformation. It is not a linear transformation. Why?
Ma'am, first property is not satisfied.
Yeah, because if you take, then first property is not satisfied. Therefore, it is actually a linear function, but it's not a linear transformation. Okay, now there are other transform like zero transformation. What is zero transformation? That you have t from v to w such that t0 is 0. Identity transformation. tv to v such that tv is equal to v for all v belongs to v. Right? And there are some properties of linear transformations. Properties of linear transformations. So if you have t from v to w and u and v, yeah, v to w and uv belongs to v, then first property that t0 is 0. Second property, t minus v is equal to minus tv. Tu minus. Actually, now onwards, whatever I am doing, I have slides for this. So even if you're not writing and you are just seeing my screen, it is fine. I'm going to share my slides with you.
Okay, ma'am.
Yeah. Because I think slides is better, because if I do some mistakes here, you can just follow those slides because they are typed ones. And if V is equal to C V1 plus C2 V2, Cn Vn, then TV is equal to C TV1 plus C2 TV2, and so on. Right? Now, example, I have a transformation T R cube to R cube. Your T100, so we can write there in this way also. T100 is 2 minus 1, 4. T010 is 1, 5 minus 2. And T001 is 0, 3, and 1. Find T2, 3 minus 2. How will you do this? This is 0, 3, 1. 0, 3, 1. See, it's coming from the last properties. You have to write TV, which is actually linear combination of Just see if you can do this. So how I'm doing this is I have a vector, matlab 2, 2. This can be written as linear combination of your basis vectors minus 2 minus 2 0 0 1, which is equal to T of 2 3 minus 2 equal to 2 T 1 0 0 0 0 plus 3 T 0 1 0 3 minus 2 T 0 0 1. Right, so T1 0 0 all are given, so you actually this becomes 2 into 2 minus 1 4 3 1 5 minus 2 minus 2 0 3 1. Okay, so now what is the answer for T2 3 minus 2 is what is the value?
770.
770.
Yeah. 770. So another example, we are just getting familiar with the matrices in linear transformation so that we can go back to image and kernel, which is actually the main part of this linear transformation. So you have TV is equal to AV, and the transformation is defined as R2 to R3, such that AV is equal to 3, 2, minus 1, 0, 1, minus 2, V1, V2. Question: find TV where V is equal to 2 minus 1. Where V is equal to this. Yeah. TV is equal to AB, we know it. So even if it is not given here, and if the question was only this question, T is a linear transformation from R2 to R3, and your AV is given as this, where V is 2 and minus 1, find TV. And part B is show that T is a linear transformation. Okay, yeah, tell me.
Ma'am, 630.
And T is a linear transformation. Right, so all we are trying to understand is the linear transformations given by a matrix. Linear transformation. So now it is understood that we have transformations from one vector space to another vector space, and these are called linear because they satisfy these two linear conditions. And once you know that they are linear transformations, then you have to understand linear transformations given by a matrix. So now onwards we are actually on transformation which is from Rn to Rm. right? And let A be a M cross N matrix. The function T or the transformation T is defined by TV is equal to AB, right? And your AV is actually equal to A11 to A1N, A21 to A2N, AM1 to AMN. So you have an M cross N matrix and you have a N vectors, right? And this whole matrix, if you multiply, becomes linear combination of those vectors. So till now we have understood this much. And I am hoping that it is clear. A22 V2, A2N Vn, AM1 V1 plus AM2 V2 and so on. So this is, you have AMN Vn.
Ma'am, can you repeat what you have written?
Yeah, I'm saying that till now what we have understood is that we have understood that we can actually transform one vector space to another vector space, and these transforming from one place to another space has some application in real life. For example, I said that when you have a image, you can actually transform it to rotate it, and so when you are rotating it, it's actually by theta angle, then that is actually a transformation. And there are many examples, like for example, if we take the probability, that also we have vectors in some space and we actually want to take it to another space. So those vectors which are 0, 1, 2, we actually want to take them to real life. So in those situations in real life, there will be many situations where you actually can transform. And there are some good examples given in those reference book notes which I have shared. So they are also taking some examples. So the entire idea of linear transformation is that you are on one space and we are actually going to another space. And these spaces going from one space to another space, there can be many transformation, but here we are only interested in linear transformations. So if we understand all that about linear transformation, how we can prove something is linear transformation and when it is not a transformation, then what we are actually narrowing down to only those transformation here we are interested, which are actually from Rn to Rm. Now these Rn and Rm are those same space from where I started today, the null space and column space, right? Now these null space and column space have two different names here, image and kernel, which I will do in next class. So those image and kernels, when we are doing is, so we now have to only take those transformation which are from Rn to Rm, and when we are on N to M space, then and when we can write this TV is equal to AB. Now how the matrix A will look like is, I am trying to show that A will always be a matrix of this type, and V will always be a vector of n dimensions, so V1, V2, Vn. And if we multiply A into V, this is actually nothing but coming as those linear combination of those vectors. So we are actually going back to from where we started, because we need a span of, that's what we say, right? Column space is actually the linear combination of those vectors and therefore it span. So that's what we are going back. And then AV is actually can be written as this linear combination. So in next class, what I'm planning to do is those kernel and images, which I'm saying that if you go from TRN to RM, so if you take this TX, this is actually the image here, and this is called, and all the images are called the range here, and this one is called your domain, this is called your range. And then if we are only on the null space as we were earlier, Tx equal to 0, then that will be making you as a kernel, and if you are taking the image, then that will is in the range space. So that I'm going to do next time. Yeah, so I hope this is all clear to you.
Ma'am,
Yes,
can you
ma'am.
just
Ma'am, I
explain
had
the
just.
question you had done?
Sorry,
Ma'am, can you just explain again the last question you had done?
the last portion about linear transformation given by matrix.
Yes, ma'am.
Yeah, so what I'm trying to say is that there can be many transformations. These transformations can be from one space to another, as we have taken example from R2 to R3, R2 to R and so on. But now what we are doing is we are only taking those transformations which are from Rn space to Rm space, because we are actually doing the linear transformations given by matrix, and we are now defining a matrix which is M cross N. So it is from where we started, right? When we were doing the null space and column space. Null space, you had n vectors, v1 v2 vn, and that could be written as linear combination of c1 v1 and so on, and that span the entire space. Therefore any vector b could be written as c1 v1 and combination, right? So that was your column space, and therefore we said the span of v1 v2 n, right? And that was about column space, and then we did the null space, which was ax equal to 0. So that two concepts are now going to come back again, and now we have a matrix which is actually M cross N matrix. And now from the above things we have seen that any linear transformation can be written as TV is equal to AV. You actually can write this way. So if we can write TV is equal to AV, A is actually of the form M cross N matrix here. And if you are multiplying with V1 this, and if you multiply at the end, what we are getting is AV, which is nothing but linear combination of those vectors. So what I'm saying is next time I have two concepts to do, which are actually main topics in linear transformation. That if you take here, so this is your domain, all these vectors. So if you take x here, tx is actually nothing but image here. And image actually is, and all the images, if I take x one vector, then tx is in Rm, it's an image. If we take all those images, it becomes range in Rm. Right, so that is what I'm saying, that now what we have to do is these ranges in Rm space, and as we have done null spaces which were tx equal to 0, so as we were doing earlier, your null space was your input because you take tx equal to 0, and column space was your output because that's what you get. So same thing is coming here, that's what I'm saying. So next time I'm doing it, image of t and kernel of t. Yeah, so
Ma'am, I had a doubt regarding the you have written T in the bracket, you have written U or V.
same, anything you write, TV or EV. TV is
Ma'am,
equal to AV, or I write TU is equal to AU. So I'm saying that TU can be, this can be written in this form.
okay, ma'am. And ma'am, in the above question also that you gave, it was U or V. Because
UV, now do you need here, V, this is here. So A,
ma'am,
V is
the above one that you gave
above
to solve ourselves.
the first three questions.
Yes, ma'am.
These three questions. Hello.
Yes. Yes, ma'am,
Yes,
you're audible. It was, I guess, below it.
this one. So what is the question? V.
Ma'am,
V.
the question. Ma'am, it had V1 minus V2 and V1 plus 2V2 on the other side.
Yeah, here. This one, this
Yes,
is the
ma'am.
question I have given. So I'm saying that you have to prove T is a linear transformation, and V1, V2 is given as V1 minus V2 and V1 plus 2V2, right? So now when you prove it's a linear transformation, you have to take two, right? U and V. So I'm saying that you can take as
Ma'am,
U1.
could you please repeat your voice? Wasn't audible. Wasn't audible.
So we are talking about this question, right? What happened
Yes,
to my
ma'am.
voice? Yeah, so I'm saying that we are talking about this question.
Yes, ma'am.
So what the question says that you prove it's a linear transformation T can be written as V1, V2, which is V1 minus V2 and V1 plus 2V2. Now to prove it's a linear transformation, what you have to do, that TU plus V is equal to TU plus TV, right? So you need two vectors. What I was saying is, then you could take U as U1, U2 and V as V1, V2. And then you can do the whole thing. If you want, I can do this question here.
No, ma'am,
Ma'am,
got it. Thank you.
I have a doubt.
Yeah, please.
Ma'am, when we take a TV equal to AV, doesn't that imply that TV is a linear transformation?
Yeah, I mean, that's what we are proving here, this question. The one
Yes,
which,
ma'am. Yes, ma'am. That's what I want to ask. Like, why
this
do
one
we?
here. No, it says that you have a transformation from R2 to R3 where AV is equal to this. Now prove that T is a linear transformation.
Yes, ma'am.
Yeah,
While assuming TV equal to AV.
because that is trivial because here you see TU plus V is actually nothing but this, and we can so this is the proof of that. In T, V is equal to AV. T will be a linear transformation. This is the proof.
Ma'am, isn't this a theorem?
Yeah, maybe it's a theorem.
Because the proof also contains the part that TV equal to AV.
Yeah, that's what they're saying. If TV is equal to AV, then it's the T linear transform.
So, ma'am, it will be independent of values of A.
What?
As,
T
as
will
we
be
haven't
independent.
used.
What is your question? T will be independent of A.
No, ma'am. As we proved, we didn't take the values of A. So it should be a theorem.
Yeah, maybe it's a theorem. You just check it in the books that is it a theorem. Yeah, you can check because there are many theorems here and I'm not including all the ones. So I'm just doing which are more important. So just check and let me also know. Okay. Anything else or I can leave the session?
Thank you, ma'am.
Thank you,
Thank
ma'am.
you, ma'am.
Thank you, man.